Now, let's move to the last part. And the last part is just a very brief, simple introduction to the concept of a graph topology. So what are the topological properties of a graph? And when we say graphs, you guys need to remember the word topology, okay? Now, let me ask you the first question. What are the differences, the possible differences between an image and a graph? And you guys can see a graph here is modeled in an adjacency matrix A. So this is a graph, and this is an image. They might look a bit similar, but what are the differences? Okay, think. Sorry?
It's only connection.
Connection. You can think about that this pixel here has neighbors, right? Maybe I will take its 4 neighbors. Spatial neighbors, right? This is my space, X, Y, my coordinate system. So I have a local neighborhood also in my, so both actually share the concept of what we call a local neighborhood. Who are my neighbors? Who are my neighbors? But you actually hold the key to the answer. It's rooted in, it's based on neighbors. Can you look, basically, let me ask another question differently. Can you look at this adjacency matrix as an image and treat this adjacency matrix as basically simply an image and perform some operations on it as an image, which means, you know, you say that this guy right here, I'll look at this, well, I'm gonna do it this way, it's easier. I know that there are many pixels, right? Okay, well, if I call it an image, I know it's an adjacency matrix, right? But can I assume this? Can I say that, for example, this guy right here, its neighbors, its closest neighbors are these 4 guys. If I reason in terms of, if I look at it as an image, right, I will say this. I will say that the neighbors of this pixel and this adjacency matrix, the closest ones, are these 4 neighbors, for example. Is that, from a graph perspective, would that be true in terms of distances? No, right? So this is what we call, this is actually the main, one of the key differences, is that in terms of images, we look at what we call a spatial neighborhood, okay? Neighborhood. But when it comes to graphs, we look at topological neighborhood. So the difference is that we cannot treat this as an image. This is not an image, the adjacency matrix. So we look at it, we need to find the closest neighbors to this node. So let's say this is my node, the white one. Okay, so, okay, let me use another color. So this is my node. To find its closest neighbors, I need to screen all the nodes that are connected to it and find the ones, for example, with the lowest distance. Okay, so maybe these nodes turn out to be these guys. This is the one, another one, and these are the closest ones in terms of distance. Okay, so they're very adjacent, they're very close. So here, the concept of spatial neighborhood does not apply, but the concept of topology, and topology basically is looking at your graph as this, like looking at the adjacency matrix and analyzing it, or displaying your graph, visualizing it, and you can see that these 2 nodes are actually very close, right? And these ones are further away, right? So this is the graph topology. It's the structure of the graph that you're looking at, and you can model via graphs or adjacency matrices. Now, let's look at the basic definition of the first topological measure, which is the degree of a node, and this is very simple. So what is the degree of a node? So given a graph G with V nodes and E edges, we define the degree of a node, or it's also called the valency of a node, V. So this is GG of V. Also, we can denote it as degree of V. It's defined as the number of edges at V. Okay, so this is also equal to the neighbors of V. And now you can see we're like looking at local topology of the graph. So for example, what is the degree of, so now I'm taking undirected graphs, but this has special definition for also directed graphs, but I'm taking the simple example. What is the degree of node V3? Guys? 1. 4. 2. We have 2, right? And this one 2, and this one is 3. So these are the degrees of this graph. And when you have a big graph, you can also plot the distribution of the degrees and see the profile, like how densely connected are some nodes, right? So we will look at this at some point. So a node of degree 0, we call it, it's an isolated node, right? So we also define the number delta of G as the minimum degree that a graph can have, and we define the number delta, big delta of G as, so this is little delta and like delta of G as the maximum degree a graph can have. And so here, if all nodes in G have the same degree K, then we call G as a K-regular graph, or simply a regular graph. So you guys know now how to reconstruct K-regular graphs. It means each node has a degree of K, okay? So let's build a 3-regular graph here. So what does this mean? It means that each node has only 3 connections. So 1, 2, 3. This one is quite easy, right? And then I need to add this. And actually, it turns out for this case, it's 2 things, right? How can you call this graph? It's 3 regular, but it's also complete graph, okay? Right, so the average degree of a graph, so this is also, it's slightly different from, it's quite, well, the average degree, you can look at it at connectance. So let's revisit how we define, how did we define connectance, guys? Anyone remembers? It's the number of edges, right, divided by the possible number of connections. So this is actually slightly different. It would be interesting to look at different graphs and plot the connectance of different graphs and also their average degrees. They're slightly connected, but mathematically they're different. Here what we're doing, the average degree of a graph is so simple, like you're just averaging over all possible nodes in your graph, and here all degrees, and you need to normalize. So we need to divide by what, guys? N, the number of nodes. Very good. So here we can write it this way, okay, the number of nodes. And here you can compute the average degree of this. So let's do it very quickly. So here we have 2, 1, 1. So 2 plus 2 divided by how many nodes? 3, so 4/3, okay? Now, there is another property here. So almost done. So what you guys know is this is the minimum degree. This is the maximum degree, and any degree of a node is basically it falls between these two infimum, like maximum, minimum, basically extremes. So the average degree quantifies globally what is measured locally by the node degrees. So it basically tells us about the number of edges of G per node. So why we say it quantifies globally what is measured locally? Can you guys understand? Because we're looking at the average, right? So remember, the degree is measured locally, but we're averaging all those local measurements at all nodes, right? So it's a global measure over the graph, but it's a global measure of local measurements, okay? So here, there's also another way of expressing this, okay? The number of edges in the graph with respect to the connectivity of the graph. So the number of edges with respect to the number of nodes. So there's this measure which we define, the epsilon of G. We just divide the number of edges by the number of nodes. So you can see that this is also another way of profiling and examining graphs. So let's look at this question. What is the relationship between the degree of a graph, okay, and the epsilon of a graph? So you guys have the definitions right here. I will give you 1 minute and you can derive the mathematical formula. So this is d of g, and epsilon of g would be the number of edges. So we have 2 edges divided by the number of nodes by 3. What do you guys know this? Yes. So so one is like basically twice the other or half the other. Yes, that's right. So if we sum up all the node degrees in G, we count every edge exactly twice. Okay? Yeah. Yes, there is no self-connection, and yeah, this is for a typical undirected graph. Yes, very true, very good. So here, this is quite simple, but you guys can think about the special cases, right? You always can think whether this formula stands for special particular cases. So here we have the number of edges is half the number of degrees, right? And then we can have the epsilon is actually half the average degree of the graph. Now, one last thing, so before we wrap it up in a bit, so the proposition, I would like you guys to think about this. I would like you to write it down and try to demonstrate it. I'm going to give you a hint, but this is one of the, I said, remember in the beginning, graph theory comes at the intersection of maths, algorithms, and learning. So here, I would like you to try to prove this proposition. The number of nodes of odd degree in a graph is always even. Okay, so look at this one. Let's check it together. So, for example, whatever the graph you're going to build, let's use this. The number of nodes of odd degree is always even. So here the degree is 3, 1, 2, and 2. So the number of nodes of odd degree is 2, right? So these 2 guys. Now, if I do it even differently, you guys can try it and play with it many, many times, right? So you can do something like this. Okay, so we have 1, 1, 2, and 2, right? So the hint is in this. It's quite simple. It's quite intuitive, right? So here, because we have the degree is it should be an integer, and we're dividing it by 2, right? So this one also should be an integer. So which means if we're dividing something by 2 and it's an integer, so this one should be what? Even, right? So we know that this is even, right? So guys, think about it. I almost gave you the solution, but I would like you to think about this. Okay, good. So this is important. I'm telling you not just for your own thinking, but these are the kind of questions you might find in an exam. Okay, good. So now the last part, this is also something to think about. It's a very famous problem in graph theory. It's called the graph coloring problem. And there is a whole book on this. There are books on just trying to come up with algorithms which color graphs. Coloring. Sorry?
coloring books?
No, not the coloring books. No, these are books on the theory of graph coloring. Yes. So actually coloring books, you can think about it that way. If you take, those of the meditation kind of coloring books, you can apply graph theory because you have neighborhoods. So each part in the figure or in the parts in which you're coloring, the parts you're coloring, you need to put some condition, which is two adjacent, maybe neighboring parts should not have the same color, and then try to recolor that. So you can model all of those books as graphs, but that's not the point. That was another example. Now, what is this problem? So in a map consisting of regions, can the regions be colored with 4 or fewer colors in such a way that every 2 adjacent regions are colored differently? So I will not give you the solution. So there is no obvious solution to this one, but I would like you guys to think about how can we tackle this problem. Actually, the first one, how can we represent this as a graph, right? How can you build the graph? After you build your graph, you represent this data, this image, okay, or this basically these sets of regions as a graph. Then the next question, how are you going to solve this problem using graphs? Okay, so I will maybe not give you an example right here, but this is something to think about, and you can explore more. There's a whole lot on the internet about this is an optimization problem, which means if you have 2 regions right here, if you colored this with yellow, let's say, and you have 4 colors. So in this case, we have 4 colors. We have yellow. It looks like a coloring exercise. There's a lot of drawing in graph theory course, by the way. So, right. So these are our 4 colors, and we want to color these differently. So maybe start with the distant ones. Or, like I'm doing it quite randomly, but it should not be random. And then see whether I can color it in such a way that at the end, 2 regions, they should not have basically a neighbor. So if I use 3 colors, would it work? Let's not use the green. Now, the problem is if I'm using this, see yellow, it's not going to work here. So I need a green right there. So with 4, I might get out. I need the green here, and I need the green right there. Okay, so think about it. Think about how to model this as a graph. Okay, great. Now, what we're going to do is that, another question, how to find the smallest number of colors. This is what we call a chromatic number of a graph, such that all neighboring nodes in G have different colors. Okay, so try to design an algorithm which uses node degree to find the chromatic number of a graph. So I have given you a hint, which is using the node degree. Okay, to solve this problem. Think about an algorithm that can solve this problem using node degrees. Okay, now the last part, and we're done. Get your brains and bees to code it up. So you guys will be using this amazing library. I really like it. It's called Snap. So this is, the Stanford Network Analysis Platform. For graph analysis, you have all many algorithms on community detection, computing the degree of a graph, finding the shortest path of a graph, detecting modularity in a graph. All these tools are already coded up in C++ or in Python, so feel free to use whichever you want. But I'm not sure that in this one, so the key thing is that first when you dive into this library, the homework for you today, I'm going to write it in an email, is that you need to understand how they encode the graphs in TXT files. So you need to understand how they represent the graph, because you can represent the graph directly as a TXT file, text file, right? Using adjacency matrix, which means I'm just reading off values, right? All these values, reading them off a TXT file. But in their representation, they don't directly use adjacency matrix. They define the graph like the node and each connecting to which it is connected, basically, based on edges. So you guys need to understand that. And what you can possibly do is try to change the code. So you take in an adjacency matrix and turn it into their graph representation template. Okay, so this is one thing you can work on, because in your projects I'm going to be giving you adjacency matrices. So it's a good first exercise for you to get, you know, like some basically your hands on the code and understand how the library works. Okay, great. So I'm going to give you an overview of this library right now. So very quickly.